joined ARUP to work on a major project, and this is what I got.
You know, there's not actually that many projects that we do that are run for as long and involve as many people. So, you know, this is the biggest I've done, and it's probably the biggest I'll do for some time.
I've got to say, it's one of the greatest projects that I've worked on. It's a sort of once in a career project.
This is the story, not of the construction of the Shard, but of the dedicated team of engineers, both men and women, who behind the scenes provided the Shard with a safe, comfortable environment, bringing this building to life.
I'm standing right at the top of the Shard, and as you can see, we've provided a water supply, and this is almost 1,000 feet above ground level. So what journey did this water have to take to make it all the way up to this level? Water enters the building from the main in the street. It comes in and it fills these tanks. We then pump it with these 75 kilowatt domestic water pumps up to level 29, which is above the offices. From there, we store it and then we pump it again up to level 51. All the time on that journey, it supplies every part of the building with domestic water, until ultimately we store it in a dedicated tank and pump set at level 67, which is purely to get water right to the very top of the building to feed that tap, which is on level 87, almost 1,000 feet in the air. So why have we put all these pumps and tanks in this building? Why not pump it directly from the basement here all the way to the top of the Shard in one go? The answer is pressure. If the column of water stands in a single pipe from the top of this building to the bottom, due to the weight of the water, the pipe at the bottom must withstand a pressure of 300 tons per square metre. That's the equivalent of me trying to hold a 4x4 in the palm of my hand.
If someone smokes a cigarette in the Shard, this activates a fire alarm system. This activation is the cause. The effect is what happens to the different systems in the Shard due to the cause. For instance, the fractures that David talked about earlier, vents open to allow fresh air to enter the building. Another effect could be the lifts entering their evacuation mode.
In a normal building, you're advised not to use the lifts in an emergency. But as we've already seen, the Shard is not a normal building. The Shard's lifts are powered up and down through the use of large electrical motors, the biggest of which is about the size of a small family car. Now, in operation, these motors get warm and they need constant cooling to run without fault, but there's nothing strange about that. But remember, the Shard's lifts need to run in an emergency, so they need to run no matter what. Therefore, the cooling system that cools the lift motors must be extra resilient. For resilience, I've designed a completely standalone cooling system dedicated solely to the lifts and separate from the main system. The system is supplied by backup power and has two of every key piece of equipment, meaning if one fails, there's always another one to stand in standby to tap in and take over. The ability to operate in an emergency means that building occupants can be safely and quickly evacuated from the building, but it also means that firefighters can use the lifts.
Another way that I've helped to ensure the Shard works safely in an evacuation is in the lift and stair pressurisation system. In this system, large fans wider than I am tall are located at each of the equipment levels, and they blow outside air into the lift shaft and escape stairs. This means that the lifts and stairs are always under positive air pressure, so when you open a stair or lift door, air comes rushing out. This in turn means that smoke is unable to enter these spaces and the building occupants can safely escape using the lifts and stairs at any time.
So here we are deep in the basement of the Shard, in the boiler room. It's quite hot, it's quite noisy, and I'm stood in front of the 4 gas-fired boilers. The installed capacity of the boilers is equivalent of about 400 domestic boilers, typical of what you'd have in your house.
To give a few examples of the types of systems that we've designed, we have to ensure that enough fresh air is fed into the building to make it a pleasant environment. Just for the offices alone, there is enough air pumped in to fill a hot air balloon every 45 seconds. We designed the systems to both generate and circulate water to heat and cool the building. We've designed the electrical power systems, taking a cable from the street of 20,000 volts and made sure that it is possible to plug in a computer, a light or a kettle anywhere in the building.
One of the interesting things about London is that you can build buildings like this and still maintain those historical buildings. So it's this interesting juxtaposition of old buildings and new buildings, and I think London's quite unique in that sense. It makes you respect some of the people that are involved in buildings like St Paul's Cathedral, because they were built hundreds of years ago without the sort of technology that we have.
Well, I hope it's still here in 200 years' time, but I think they'll be, I hope they're still impressed by what we've done, more than anything. There have been so many occasions on this project that we've gone further or done more than you would normally do, or innovated, and I hope that it sort of marks a line in the sand as a sort of, yeah, that's the new standard, and buildings forward take that on, and that becomes normal.